Our 4.1 self-test. Just a little bit of work to make sure we understood the ideas that we went over on whatever day that was. Friday? Yeah, I think it was Friday. All right. Let's just go through these slowly here. First question is, what is meant by a hydronium ion? All right, so just to remind you guys, this means that we had a water molecule that took an extra proton, an extra hydrogen ion. And as a result, it's H3O, but that proton had a positive charge. So it adds an extra positive charge to a water molecule. And so if you drew that in space, it would look like an oxygen with 3 hydrogens bound to it instead of 2. And the whole thing would take a positive charge. Now, these square brackets are sometimes used when drawing out a molecule or ion or an atom when that value has a charge on it. And it doesn't mean concentration. So while we use square brackets often with, say, symbols to represent concentration, this really is just a way we use to indicate the whole thing takes a charge, and that positive charge is sort of spread evenly throughout. Sometimes a positive charge is localized in a certain area of like maybe just this hydrogen, say, takes a proton, or pardon me, takes a positive charge and holds all of it there. But in this case, it might be spread equally between all 3 of these hydrogens. So as a way of demonstrating that, there are other ways to demonstrate that more specifically that you may learn in later grades. But that's how we show it here. Anyhow, that's what's meant by a hydronium ion. All right. So we'll move on to the next question, which is also question 1, which I hate. I hate questions. I hate it when I do that. So we'll change it to question 2. All right. Complete the equations for the ionization, also known as the dissociation, of these acids in water with a Bronsted-Lowry view of acids and bases. Meaning, when we say Bronsted-Lowry view, I'm going to highlight that. So what that means is that there is a proton transfer from one substance to another. That means proton transfer. And one substance is a proton donor, and the other is a proton acceptor. All right, and we're looking at the ionization of acids. This is, actually I don't remember the name of that one. I'd have to look it up. Chlorous acid? I'll take a look here. Doesn't really matter, but now that I tried to say it, I should probably figure out how to say it. HClO2. Hypochlorite, probably. Oh, chlorite. Ic. So that's chloric acid. Okay. Chloric acid and water. All right, so what's important is this proton from the acid is going to be donated to the water because acids are proton donors. So the result is we're going to get a ClO2 minus charge, which is also still going to be aqueous. And this extra proton is going to be passed on to the water molecule. And so we get this hydronium ion as a result. And this water is, in this case, acting like a base as a proton acceptor. Yeah, I was just about to use it, actually. It's all fancy. And I think I left my sheet in here, too. I'm not so sure about that, sir. But I'll take a look right here. Justin, Emily, Liam, Mac, and Emily again.
So it must be with me.
Okay. Must be with you. All right, can you lock the door behind you? Or close the door behind you? That's fine. Thank you. Sorry about that, guys. All right, so hydronium ions are also aqueous. Okay. And that's all we really need to do here. So we have proton donation in this reaction as well. We have a hydrofluoric acid. It's going to donate a proton to water. And as a result, we're going to have some fluoride ion just kicking around. And a hydronium ion. Oh, it's still locked. All right, pardon me. I got to go get Logan.
No, that's fine. What up? I know. Okay, I realized I actually left my jacket in here.
Oh, you did? Yeah, it's right there. No problem. And hydronium ion is also aqueous.
Okay.
Yeah, it's fine, Logan.
Now you will be disrupting.
All right, sir. Take care. Okay, this is... Man, I forget the name of this one. Is it formic acid? Acetone. Is it acetone? Oh, shoot. I think it's formic acid. All right, anyways, doesn't really matter. So one of this is an organic acid, COOH, which means it's going to donate a proton to this H3O. And so we're going to get this HCOO. I guess that makes it formate, an aqueous ion, and a hydronium ion. Okay. All right. So that's fine. Now next, we have questions, which I guess I should rename 3 and 4, which ask us for both the Arrhenius definition and the Bronsted-Lowry definition of acids and bases, and just talk about how they differ. So an acid, as far as Arrhenius was concerned, is a salt that when it dissociates, releases a proton, or H+, into the solution. All right, and a base is a salt that when it, so maybe we'll do an example here. So an example would be H3O. Nope. Let's do H2SO4. Releases 2 protons and 1 sulfate. All right. So a base is a salt that when it dissociates, releases a hydroxide ion, which is also known as an OH minus, into the solution. And so, for example, we'd have magnesium hydroxide, which we all learned about recently, making a magnesium ion, which is fine, but 2 hydroxides. And the hydroxides make something basic. Now, Bronsted-Lowry definitions include all Arrhenius acids and bases. However, some other things also end up acting like acids and bases sometimes. So very more basic, a Bronsted-Lowry acid is a proton donor. So anything that acts as to donate a proton in a solution. And so we can look back at our definition as where this was introduced. So Bronsted-Lowry acid donates a proton to a water molecule, or I guess I should say any other molecule, creating a hydronium ion. The proton donor, period. That's fine. So for example, I'll just choose NH4 plus ammonium plus, we'll imagine it's mixing with water, and it's going to donate an extra proton to water. And it will form NH3, a neutral charge, but pass that positive charge and that extra hydrogen over to the water to make hydronium. Okay, and a base is a proton acceptor. So for example, in this case we have the acid here. Now if we look at the reverse reaction, the hydronium ion is donating a proton to our ammonia to make ammonium, and so that makes this guy the acid in this case. Now in this same exact example, we'd have in this case water acting as a proton acceptor, which makes it a base in this case. And in this case, the reverse reaction, the ammonia is acting as the base. Alright, so we're going to repeat our habit of looking at these reactions in this way. Alright, so what we have here is, what is this, benzoic acid? Whatever, who cares? So it looks like when we look at the reaction, this guy loses a proton. So these guys are similar in some way. They're actually a conjugate acid-base pair, but we're not really asked to compare them using that lens yet, but we'll come back to that in question, which was labeled question 5, but we're going to call it question 6. Alright. So it looks like in this reaction we have a proton being transferred to the carbonate ion. And in this case, we have a proton being transferred from this bicarbonate into this carbon ring here. Okay, so I'll use a different color here. So as a result, because this guy is donating a proton in this case, we're going to call him an acid. And these guys accepting protons, we're going to call him a base. And this guy, the bicarbonate, is now donating an acid. When we move left in the backwards direction to form these guys again, because they live in equilibrium. This guy's accepting, so we call him a base. All right, next question. So again, it might help to see which two species correspond with each other. It looks like this guy gets an extra hydrogen and an extra positive charge. I can tell it's an extra positive charge because adding a positive charge to a negative charge gives us a neutral charge. And these guys will also correspond with each other. It looks like in this process, this guy loses one hydrogen and also loses a positive charge to give him a negative charge. So as a result, it looks like the proton is being transferred, in this case, from the sulfurous acid to this, I don't remember how to say that. The nomenclature is not very interesting. I wouldn't encourage you to spend a lot of time worrying about it beyond a functional amount. Alright, so that's fine, and in this case it looks like this proton gets transferred in this direction because if I'm going to go in the backwards direction, I notice this guy has one more proton than he did in this case. So he's going to lose one, and this guy has one more proton here. It's going to gain one. Alright, so proton donors are acids. So this guy's an acid. And this guy's a base, because he accepts a proton. This guy's a base, because he accepts a proton. Alright. Alright, moving on. So lastly, we identify the conjugate acid-base pairs in the following reaction. Okay, so we're going to start by figuring out, well, which things correspond. So you guys are a pair because, as we can see, there's an increase in proton, but other than that, everything's pretty much the same. Same with these guys. Alright, and so that means that we should be gaining a proton to get from here to here, which means we're going to suck one away from this sulfurous acid. And as we can see, the sulfurous acid lost a hydrogen to get to this form. Now, if we go in the reverse reaction, it looks like hydrogen is passed from this ammonium to this guy, H+, like that. Alright. And so that means that we have this guy as acting as a base because he's accepting a proton, while this guy's an acid, he's donating one. This guy's an acid in this case because he's donating a proton, and this guy's a base. Okay, so our first pair of conjugate acid-base pairs could be our ammonium and our ammonia and our ammonium. So it'd be NH4 plus and NH3 is our first pair. And the next pair is these guys. The acid in this case is our H2SO3, and our base is our HSO3 negative, like that. Okay, so we're going to see if we can go through a similar process here. These guys correspond, as I think you'll be able to tell. Some oxalic acid and some, I don't know, oxalate maybe? No, probably some weird name like bioxalate. Alright, so first things first, we decide which guy gains a proton. Looks like this guy loses a proton going from here to here. And looks like this guy gains one. So we'll say this guy is transferring a proton. And in the reverse direction, looks like this guy is losing a proton to form this one. So we'll go back and we'll label which one's an acid. Acids donate, lose a proton. This guy's an acid. And these guys that accept are bases. And as a result, our conjugate acid-base pair, our first acid is this oxalic acid, H2C2O4, and base, which is HC2O4 minus. And pair 2, our acid looks like our phosphate, phosphic acid, phosphic or phosphoric, H2PO4 minus. Wait, hang on. Is that charge right? Yeah, that charge is right. Okay, cool. So we'll look lastly. Got some acetic acid here, which corresponds with this acetate. And this oxalic acid here, which I don't know what it makes. Don't know the name of that one. Alright, so looks like in this interaction, this acid passes a proton to this guy to make a full H2, and when we look in the reverse direction, these two combining to form these two, it looks like a proton is shifted from this guy to this one. Alright, so acids donate, so we have an acid here, and an acid here, and bases accept protons, so this is a base, and this is a base. Alright, and so we could say we have our acid base pair here. That's our first one, a CH3COOH, an organic acid, COOH, and a base, CH3COO minus. And then we have another acid-base pair. In this case, the acid is H2C2O4, and the base is HC2O4 minus. Alright, so let me know if you have any questions about any of those. And we'll be moving on from this material tomorrow.